Welcome back, everybody. I hope that you had a good break. I sense, so we had a lot of interaction. I sense that some of you, it's Friday, so let's have a bit of distraction and ask a few questions for a few minutes, and then I'd come back to you. So I think I have, but maybe not that yet, probably this one. All right. There you go. So let's just practice a little bit. So this is a standard inverted index. And I have to locate it again. I think it's that one. Yes. So this is a standard inverted index that was built from a collection. I'm assuming here more formally that the terms are ABC and so on. The document IDs are integers. So what documents does the query A and B return? So these are the four possibilities. So these are the lists of documents, A and B. The answers are still coming in. $30, make it 30, 30. Okay, 30. And so the correct answer is indeed 3 and 8. How did I reach this? This is the intersection of the two, right? 3 is here and here, 8 is here and here. So it means that both documents 3 and 8 contain A and B, right? And the answer 1, 2, 3, 4, 5, 6, 7, 8, 9 would be the union, but that would be A or B, right? To get this one. Okay, so this is first one. Here's another one, that's C or D. Right, so these are the four possibilities, C or D. Right? And here you said, wow, I love that, 100%, you got it. So 1, 2, 3, you see 1, 2, 3, 4, 5, 7, 8, 9, just 6 is not in there, indeed. And you see, so never make the mistake here. The first one is really the document frequency. So this one is not a posting, right? This is very important. This is why I put it on a black font rather than a white font, just to make it different, right? So these are the postings right there. And you see the postings are ordered, right? It's always in increasing order. All right. What does D and not E return? D and not E. So that's also an intersection, but you need to flip the posting list on E. Let's try 100% on that one too. the answers. Yes, you are fantastic. 1589. So indeed, you see that's D here. So it's a subset of that, and the 3 goes away. So you need to basically use this as what you remove. So 3 goes away and none of the others. Yes. So now you see you can do N or not in general, and you know the trick. If it's a more complex thing, just bring it into the conjunctive normal form, right? And within an and you have ors and nots, right? Then you can go via starting with the shortest posting list and increasing. But since you know how to do it, then what does A or B and E and F or not G return? So of course, you can either go algorithmically and really try to do it the way the computer does, or you're a human being, so you can try to also find tricks to make the answer faster. Like, how can you optimize this? This is already in a conjunctive normal form here, so that should help. Takes a bit more time, right? This one. Right? Let's see. Slightly lower answer rate, so 77%. Let's go through it, right? So first, the easy part, right? So it's n, right? And the easiest factor, n is like multiplication, so we can say factor, is E, right? So 2, 3, 4, 7, since there's only n's, it's anyway going to be a subset of these, right? There's going to be nothing else than these 4, but it might be less than these 4. So then we can just go through them. It's only 4 of them, right? So we just need to check that each one of them is both here and here. So 2, let's start with 2. 2 is in here, so that satisfies A or B, and 2 is in F, so that satisfies A or B. So 2 is in the final results. 3, what about 3? 3 is in here, so that satisfies this part. And 3 is not in F, but it is in G, so that doesn't satisfy F or not G, right? It's neither in F and nor is it not in G. So 3 goes away. 4, so 4 is in here, so that takes care of A or B, and 4 is in F, so that takes care of F or not G, so 4 is fine, 2 and 4 so far. And what about 7? 7 is in here, so it satisfies A or B, and 7 is not in F, so you can forget about that, and it is in G, so that also doesn't satisfy not G. So for this reason, only 2 and 4 survive and are the final results. Okay? So this is the reason why it's only 2 and 4 and 3 and 7 are not part of the results. Okay. Another one. Which of the following is not an encoding? I'm even showing you the intermediate answers so you can see what you answer. So there is a majority. The question is the majority correct? Which is sometimes the case, sometimes not the case. You can still change your mind. All right, so in that case, it's not the majority who was correct. It is indeed Unicode, because Unicode is only a catalog, that's all. All it does is list the characters and say this is character number 1, this is character number 2, and so on, right? So Unicode is not an encoding. UTF-8 would be an encoding based on Unicode, just like UTF-16 and so on. ASCII is an encoding. macOS Roman is also an encoding. Might no longer be really in use, but this is actually an encoding. Okay, so this is another one. Which statements are correct? Index expansion takes more space, but queries are faster. Index expansion takes less space and queries are faster. Query expansion takes less space, but queries are slower. Query expansion takes less space and queries are faster. Remember that expansion is for the asymmetric case, right? In the symmetric case, you have an equivalence relation and then you have these groups. So you have the normalized types. But in the case that the relation is asymmetric, then you need to use expansion. The equivalence classes no longer work. Then we saw you can either expand the query or the index. Almost at 30. We have a majority, and the majority is correct. So what you need to see here is something very general about indices and in general performance. The performance of an algorithm is basically once you know the query, once you know what the user wants, how much time does it take and what complexity does it take to answer to the user. So it seems easy, but what makes it more complicated is that you can increase performance by doing some work ahead of the query. That's exactly what an index is about. It means that before the user even tells you what they want, you build a structure that is prepared for any case of what the user wants. This is why we have the standard inverted index. And what happens is that there's no free lunch in computer science. This is how it works. If you want something faster, there has to be a cost somewhere. And the cost will be both in terms of time and space. It's going to be in terms of space because these index structures that you build at compile time or before the user builds their query, it's up space, right? If you want to build up a search engine like Google, you're going to have a lot of space needed in order to put your index in there. And then this is the magic of how when you query, then in just a few milliseconds, you have the result on your screen. That's because there is all this index structure. The second cost is in time, because actually building the index is going to consume time. And so the difference between index expansion and query expansion is exactly about where you put the slider between the two. Do you want to save a bit of space? Then you can keep the index as it is, but then you're going to pay it with more time at runtime, right? Once the query comes in. Or do you want a faster query, but then the costs for that is going to take more space to expand the index and maybe even more time to expand the index, right? For whom is that clear? All right, as expected, because the majority got it correctly. All right. So this is really this idea between, there's many ways of calling that. There is compile time versus runtime, static versus dynamic, and so on, right? So there is what is done before you know the query and what is done after you know the query. Okay. This is true in databases, this is true in programming languages, and it is also true in information retrieval. Okay. And that I already, I don't think I need to ask it again, because I asked you for ideas how we decrease the false positives with phrase queries. Okay, so now I'll get back to the slides. And if I prepared it nicely, it should put us exactly where we were. And it's recording. Just need to wait until the slides are opened. Yes. Okay. You have just half an hour, then you can go for lunch. So we stopped here at binary search trees. And again, don't forget the goal of that is to have a data structure that is going to help us when we query, when we go through the standard inverted index to look up the terms. Okay, so it's a binary tree because there are at most 2 children. In fact, it's a perfect one. It doesn't have to be perfect, but because it's perfect. And it's a search tree because we have some labels on the nodes. These labels are in a set that is ordered. It can be numbers, but it can also be words that are alphabetically sorted, like in a dictionary. And you have this criteria that every time, everything that's on the left comes alphabetically before the label of the node, and everything that's on the right subtree comes after that, right? Now, that's kind of helping us, right? Because now we have a tree that is kind of sorting an alphabetic list of terms, but in a structured way. And now we could just plug it into the standard inverted index and just, if we have all the terms organized in a tree like that, all we need to add is the postings list, right? If every node gives us a term, we just add a pointer and to the posting list, and that's O of 1, then to follow the pointer, okay? Now, if I rotate that by 90 degrees, then this is what we get, right? And now we have our standard inverted index with this enhanced structure on the terms, and that is implementing a binary search, as you said earlier. Okay. Now, there are a few more things that we are going to do, because we are not quite there yet. The first thing, if I go back to that view, I rotate again by 90 degrees. The first thing that I'm going to do is to no longer assume that the terms are on every node, leaf or not leaf. I'm going to assume that the terms are all on the leaves in here. And the leaves point to the posting list. All of my terms are on the leaves. And the nodes that are not leaves, they are here for the binary search, but they are not actually terms or anything that would link to posting list. It's just for helping us search. So I put some random letters in there like O, J, S. So this is now leading to two different colors, right? I have the leaves and I have the non-leaves or non-terminals, you would call them also for context-free grammars. Now, in practice, I just put letters in there as an example, but in practice, when you want to build a tree like that, you will still reuse the terms. And what's going to happen is just for convenience, because the problem with using this is that you need to come up with random strings that come in between. But in practice, what we do is that we take here the smallest value from the right, that would be not, here the smallest value from the right, and here the smallest value from the right would be this one, right? And that gives us close and open intervals. Basically, it means that everything is strictly before or, and everything there is equal to or after or, right? And we have this rule. Again, all of my terms are on the leaves, and I'm reusing some of them, but this is only for the purpose of the binary search that I'm putting them here, okay? Who would be able to build a tree like that? Okay. So in that case, it's perfect. In practice, it's not going to always be perfect, right? You might have not the full last level like this. All right, so this is one small change that we did, that we only have the postings lists at the leaves and the other nodes are just for the binary search. Now, here's an example. So here, this is the convention where I have posting lists everywhere, otherwise it would be too big. But how do you see now the binary search? Well, imagine that I have to look for should now. So I start here and I compare. So I have a first comparison. Should is before, so I go on the left. Should is after Merli, so I go to the right. Should is before that, I go to the left, and there I found it, right? So that would be the case where they are posting lists everywhere. If they are not posting lists everywhere, but only on the leaves, then you would always go all the way down to the last level, right? So you see really these two conventions. Convention one, you have posting lists everywhere and the terms are everywhere. Convention two, you only have the posting lists and the terms at the leaves, and on the other nodes, it's only for the binary search. That's, who is with me? Okay. It's going to increase in complexity, right? So I take it step by step. Oh, I should have asked you, but you already told me earlier that it's logarithmic, right? So the binary search is logarithmic. So it's a lookup in a binary search tree. Okay. But I said earlier that we have, in fact, B+ trees. This is what we have in the end. So how does it differ from these binary search trees? What is the difference between this and a B+ tree? Well, what we are going to change here is that we are going to allow for more children than just 2. For example, I could here have 3 children, right? Be, let, and not. And then we need, instead of a single label, I need a label for every interval, right? So I need a label between the first and second child and another label between the second and third child. But I still have this rule because of my ordering that everything on the left of let is strictly before let. Everything on the right of let is equal to or after let. Everything on the left or not is strictly before not, and everything on the right or not is equal to or after not. Who understands this one? Already sense? Okay, awesome. So this is what happens if we add more children. We allow for more children. Of course, it's no longer a binary tree, right? Because we have more than 2 now. Why do we do this? Well, it has to do with the hardware level and the physical implementation level. And some of you already had it in mind, like, for example, your colleague on Zoom who mentioned cache locality. In the end, this gets implemented on actual hardware. It's not just mathematics hanging in the air. It's really an actual drive that is going to store this. And what you need to understand is that if a tree like this is small, it will be fully in memory, in working memory. If it's fully in working memory, then that's easy. That's random access. You can access any place in memory in O of 1, all you want, right? But the thing is, it's going to be a lot of terms. It's going to be a lot of documents. So what happens in practice is that it will not fit in the memory. It will not fit in the RAM of your machine. What that means is that you will have to output some parts of the index to the disk. Now, if you put it on the disk, it means you will have to read it from the disk. And you have to read it from the disk. You know that you cannot read bit by bit. If you read it from the disk, you need to read blocks. And the size of a block on a typical computer nowadays is roughly 4 kilobytes, right? So every time you read something from your disk, you are going to read 4 kilobytes. Now imagine that we have a binary tree like this. These are very small nodes, right? So how do you organize physically on the disk? You would have to basically store plenty of nodes in the same block, one way or the other, right? But basically, the logical structure here is much more fine-grained than the way you read from the disk, with much larger blocks. So the reason we increase the number of children is that we would like, in the end, to have a closer match between the nodes and the blocks. We would like, ideally, that a node corresponds to a block. It's a coarse way of saying it, but this is the reason, right? So we want larger nodes so that we can read more together. Then you can read at the same time, you load from disk this entire subtree like this, and you're compatible with block access. For whom does that make sense? All right, so this is really motivated by hardware. You know, if we had a different computer architecture and we could read everything from memory, then maybe a binary tree would be better. Okay, but from disk, we want more children. So that's an example of B plus tree, because this is the name that it has, it's a B plus tree. Now you see, if you look at the number of children, you can see that they are here. 4 children, 2 children, right? So basically, in a B plus tree, all leaves are at the same depth here. You don't have an imbalance, right? Everything is at the same depth. You have a layer, a second layer for the search, and then the leaves that have the posting list, right? This is what the B plus tree means. When you have B plus tree, it means these are where your terms there and posting lists are, and this is for the search. If it's a B tree, you don't have the plus in there. If it's just a B tree, it means you have them everywhere. That's the same distinction I explained earlier with binary trees. So I'm focusing on B plus trees. So this is where my terms are. And you notice here that this is repeated here. It's the leftmost from the right merely that comes here, and that's only for comparison purposes. Here you have a posting list. And then you notice that all non-leaf nodes have between 3 and 5 children. That's kind of a constraint of the tree. So 4 is between 3 and 5, 4 is between 3 and 5, and 2 is between 3 and 5. Don't see anybody react. 2 is not between 3 and 5, right? So the root is an exception. For the root, it's fine. It can have less than 3. It cannot be more than 5, but it can have less. That's the only node that is authorized to break the lower bound. But everywhere else, it's between 3 and 5 children. Here, I'm repeating what I said. The actual terms of the standard inverted index and the posting lists that corresponds to them are only at the leaves, and the other nodes, the non-terminal nodes, they are only here for the purpose of searching and looking up in logarithmic time. Now, this between 3 and 5 that I told you, it's one of the parameters of the B plus tree, right? You have these constraints, and you will understand why we have these constraints when we actually build it. I will have an animation. And so, for example, here, that's a B tree without the plus. Without the plus, it means that any node can have posting lists and terms. That's the difference. And 2, 4 means you have between 2 and 4 children per node, except the roots that can have less, right? So this is a 2, 4 B tree. Now, the plus in B plus tree is like this premium or plus. When you subscribe to streaming services, they all end with plus, giving this feeling of extra features. And there are even indeed extra features in a B plus tree. For example, one of the extra features that you get is these pointers that organize all the leaf nodes into a chain. And why is that good? It means that thanks to these extra pointers, we can in fact start here and traverse all the way all the terms like this. It's very practical. It's really a chain that goes all the way. So if you start somewhere, you can easily traverse backwards or forwards in the list. You cannot do this with a B tree, but with a B plus tree, you have this nice feature of the leaves. So this is one extra nice perk of the B plus trees. We will see again later why this is useful for some of the features we will want for our search. Now, I would like to say more about the parameters. So in the general case, when you categorize the B plus trees, one way of doing that is that the parameter is D, it's an integer, and then you say, okay, the number of children has to be between D plus 1 and 2D plus 1. For example, if D is 0, then that's a 1, 1 B plus 3. If D is 1, that's a 2, 3 B plus 3. If D is 2, that's a 3, 5 B plus 3. If D equals 3, that's a 4, 7 B plus 3, and so on, right? You just instantiate by putting whatever value you want for D. Now, in practice, it's going to be more like that. You will easily have dozens, maybe even hundreds of terms in the nodes, but it wouldn't fit on my slides. So this is why I keep it to smaller integers, right? Now, this is a matter of convention, because what makes B plus trees a bit difficult to teach and to build in general is that there is no real standard convention that everybody in the world agrees with. So I picked one for the purpose of the course. But you will find people who don't say D+1 or 2D+1. They might say D+1 and 2D, or they might say D and 2D and so on. So there's varying conventions, but I stick to that one, to keep it simple for you. There are other people, when they say here, when I told you 4, 7, it means that you have between 4 and 7 children. But for some people, they don't mean between 4 and 7 children. They mean between 4 and 7 values on the nodes. But now I need to explain to you why it's not the same. There is an offset of 1 between the two. If you have n trees in there, n, so in that case, n is equal to 7, right? How many intervals do you have between the trees? So now we were discussing earlier with Marco that you could have hammocks. How many hammocks can you put between the trees if you have n trees? Or if you have n posts, how many fences can you put in between? Yes? N minus 1, exactly. So this is something that once you know it, it's easy, but if you don't think of it, it's easy to make mistakes. So if you have n trees, you have n minus 1 intervals. But this is important because if you have 3 children, it means you have 2 values, 2 labels in there. We can call them keys if we want. If we have 4 children, then we have 3 values. If we have 5 children, we have 4 values. So do you see now that if I say between 4 and 7 children, I mean between 3 and 6 values per node. Who sees it now? Who doesn't see it yet? Okay, so I assume you don't see it yet? I can re-explain easily, right? I assume there are many other people who probably didn't get it the first time. So here, if you see that you have, let's say, 5 children, these 4 values here, they allow us to compare. If we have 1, imagine that it's real numbers, right? Everything here would be smaller than 1. Everything here would be between 1 and 2. Everything here between 2 and 3. Everything here between 3 and 4. And everything larger than 4. So it means that if I have 1, 2, 3, 4, 5 children, the number of keys I'm going to have is 1 less. I'm going to have only 4 keys for 5 children. So now, if I have between 3 children and 5 children, it means that I have between 2 and 4 keys on my nodes. This is what it means, right? And so what I was saying is that when people say on the internet like a 4-7 B+3 or a 3-5 B+3, you have to be careful because some people mean the number of children as the allowed interval, and some people mean the number of keys. And that makes it very easily very confusing to follow. So this is why, to make it easy for that course, I just pick one convention for us that whenever I say a 4-7 B+3, I mean the number of children. And I use this D+1, 2D+1 convention. You just need to be aware that there are others, and this is just for the purpose of the course. Who is with me? Yeah, awesome, perfect. All right, that takes care of it. All right, so if you have D+1, 2D+1 for the children interval, then you have between D and 2D for the number of keys. All right, so let's take a 3-5 B+3 and have an animation for you to show you how that actually works. And you will see it looks easy, but if you start to want to implement it, you will see how complex it is. This is the reason why we will not even ask you to implement one. That's very, very complex. You will run into plenty of issues when you try. So imagine, like any search tree, what happens is that you add and add and add. So you insert in the tree, and then you can look up, and then you can delete, right? These are the sort of operations you can do on a tree. So I do that. Imagine that I have a stream of terms. I use integers here, so a stream of integers that arrive and that I insert into my B+3. For the purpose of the animation, I'm just going to take increasing integers. But in practice, it can be any integers in any order, right? These are just when you build the index, the terms in the way they arrive. So we have 1. This is a B+3. It's a 3-5 B+3 because the root can have less than than the number of children. So it's totally okay for the root. And we have only one node. It turns out to be a leaf. So the root is also a leaf. There is a single term, and it probably points to a postings list. Now we add a second one, right? So now we have two values in there. Now remember, I picked the 3-5 convention, so it means the number of children is between 3 and 5, and that means the number of values is between 2 and 4, right? Just an offset of 1. So between 2 and 4. And here it's between 2 and 4, so we are fine. Then let's get another value, 3. That's still between 2 and 4, the number of squares that I have in here. Then another one, 4, still between 2 and 4, but now I'm slowly reaching the capacity, right? So it's 4 values. Now I add a fifth one. Now we have a problem, because I told you between 3 and 5 children means between 2 and 4 values, we have 1 too much. Who agrees we have 1 too much? Okay. So what do? We split it like this. So we just make 2 nodes out of it, one that has 1, 2, 3, and one that has 4 and 5, and we add a new root node. And again, the easiest is to just take the leftmost value from the right, so we take a 4 in there. Now we have 5 terms with their posting list and an additional node at the root that has a 4. Now you see the root has 1 value which is less than 2, and it has 2 children which is less than 3, but again, the root is an exception. So if the root has less children, that's totally fine. It's the only one that is allowed to have less. And now you see how the NAS trick, this is the reason for this D+1, 2D+1, because now when we had 1 value too much, splitting it in 2 is going to bring us 3 on the one hand and 2 on the other hand, and 3 is between 2 and 4, and 2 is between 2 and 4. So basically, as soon as you have 1 too much and you split it, you get back within the boundaries of what is allowed. This is the nice thing about the way this construction works. Let's continue to add. 6, it fits. 3 is between 2 and 4. Number of values. 7, we have 4 values, so that's between 2 and 4. And we add now 8. Now that's too much. Now we have 1 value too much, right? That's 5 values. Virtually, I mean, there's no children, but if there were children, you would have 6 children in here. So that's too much. What do? We split. Right? And we are going to use 7 as the value in here, and that goes into the root. Now we have a root with 3 children, 2 values, 4 and 7, and 3 leaf nodes. We continue to add 9, still okay, 10, still okay, 11, that's too much, so we split. Now we have a root with 4 children, 4 leaves like this. And again, 3, 5b plus 3 still satisfies the constraint. And now I fast forward a bit because that's going to be boring. So now I go all the way to 16, where now I have a root with 5 children, and I have 5 leaves like that. Now imagine that I add 17 here. That's the new number that arrives. Now that's too much. So what do? I split it, half-half. But now you see something is happening that's new. Now it propagates. The problem only shifted. So now it was too much here. Now it's too much there. Right? So now the root is too big. It has 1, 2, 3, 4, 6 children. That's 1 too many. So now we split it, and bang, that's how you get yet another level. And you see, as it grows, the height of the tree is going to grow naturally whenever you split the roots. Right? And then 18, yeah, you can continue. Who gets the logic of that? Okay, so this is the particular example where you have increasing integers. In practice, it can be in any order, but basically there is an algorithm to insert. And again, it's complex. If you try to implement that and have arbitrary insertions and so on, you will quickly see that it's much more complex than it seems to implement, right? But at least you get a visual. Now, what if you delete? Well, if you delete, you just need to check every time that you are between 3 and 5 children or between 2 and 4 values. So here it's still okay. Here it's still okay. Now that's 1 too little. 1 too little. So what we do, instead of splitting, we merge. Now if we merge, now we have a problem again. We merge again, right? So you see, it automatically grows and shrinks elastically as you insert and remove values. You just need to make sure that whenever you break the rule of having between 3 and 5 children, or 2 and 4 values, you need to merge or split the nodes. Okay, so that's my animation to give you an intuition behind that. So now it means that you have this structure, you can create it and build it by adding more terms, you can remove terms, so it can have its own life. And now what's going to happen in terms of what do you store where, you really need to keep in mind that all the parts at the bottom is going to be stored on the disk and kept on disk. And the part here might be stored on disk, but at least you load it in memory, right? So you can assume that the upper part of your B+3 is in memory. So the first pointers are going to be followed in memory. And then when you reach a certain level, this is where you start reading from disk. But it's efficient because since we have these big nodes that match the size of the blocks on the disk, reading them is actually efficient, right? And then we can load just what we need from the disk. For example, we could load just that from the disk with the postings list, right? Who understands that? Okay. So that's the idea. So now we have an efficient structure called the B+3. It's not just used for information retrieval, it's also used for relational databases. So you might have heard also about it via a relational database systems course. Who already saw B+3s before? Some of you, all right. Okay, so that's it. Now we have a data structure. We can use hash maps. We can use B+3s to allow for scaling a little bit. What happens if it doesn't even fit on disk? That we'll see in a few weeks, right? So this is also something we can solve. But now we know how it works if it doesn't fit in memory. 3 minutes left. Maybe I will just show you an appetizer for what we'll do next time. It's the wildcard. What if you want to query not specific terms, but match any sequence of characters? So here it's a bit like regular expressions. You can think about that. It's a dot star. So for example, imagine that you want Zurich, but you want the High German version, the Hochdeutsch version, or UE, instead of the umlaut and so on. So multiple spellings. You could even imagine a star instead of CH if you want to catch the Zurich as well. But basically, this is a feature of an information retrieval system that we also might want to have. So how do we implement that kind of system, right? For example, you can use the star for word families. You want to catch, for example, informatics, information, informative, and so on with a single query, and then you just say informat star, and that catches everything. But now the question is how we implement that kind of queries. And the answer to this, I will give you next week, how we can use everything that we've built in terms of indices to evaluate these queries. So before you go, just want to check. I need to find it again. Here you go. How much did you understand? That's your way of telling me slow down, slow down, slow down, or go faster, go faster, go faster, right? That sounds about right. My goal is always majority between 80 and 95. All right. It also shows you how you stand in level of understanding. So I'm glad to see that there are a few who understand everything. That's wonderful. Everybody should read the book. That's again an additional chapter. If you understand less than 80% or less than half, don't worry. We are here. The TA team is here. I'm here. You can send us emails. You can talk with your colleagues. You have the chat, the Element chat, where you can ask questions. There is the Moodle forum. So we are here to help you and to make sure that everybody is following. So thank you very much, everybody. I hope you enjoyed today's lecture, enjoyed the exercise classes on the topic of languages and what we covered last week in the lecture. Enjoy your weekend, enjoy the exercise session. See you next week at 10 a.m., same room, same day. Thank you.